Okay, I wanted to quickly go through the devoir. This is for the homework problems. Actually, I gave you a problem about 2 weeks ago, which isn't in the list of problems, but I forgot about it last time. But in case you were doing it, this had to do with, I said you had a phase diagram, system AB, and here you have a miscibility gap, liquid and two liquids, and this is T critical and X critical, and I said, assuming that it's a regular solution, obtain an expression for the critical temperature as a function of the regular solution parameter. Okay, so remember, a regular solution is delta G of mixing, the Gibbs energy of mixing. For a regular solution is the ideal term, RT XA ln XA plus XB ln XB plus a strictly regular term, which would be omega XA XB. So that's the omega is a constant independent of temperature and composition. That would be a strictly regular solution. Now if omega is positive, you have a positive excess term. And so you will get, as we said, like on this figure 18, you will have this, the Gibbs, you'll have a miscibility gap, and your Gibbs energy curves look like this. At low temperature, you'll have a bump, so low temperature, say at 1,000 degrees, the curve has this shape. So there's a common tangent between the two sides of the curve, which gives you the two-phase boundaries. And at lower temperatures, the two-phase boundary gets wider. At high temperatures, beyond a certain point, the curve is completely convex, and now there are no common tangents. So now you have a complete miscibility, right? So this is not a regular solution, but if you have a regular solution and omega is positive, you're going to get the same thing, except now, of course, the X critical will be clearly at 50%. The system, if you plotted the Gibbs energy of mixing curve, the Gibbs energy of mixing curve is going to be symmetric about 50%, simply from the symmetry of the equation. Okay, so what we're trying to find then, so if temperature's low enough, the curve looks like this. If the temperature's higher, the curve looks like this. And you want to find the temperature at which it goes just from this to this. And that, how do we find that? That is then clearly the temperature at which the second derivative of this curve changes sign. The second derivative is the rate of change of slope. Here the second derivative is positive. Here the second derivative is negative. So you're trying to find the temperature where the second derivative is exactly 0 at 50%, and that will give you the critical temperature. So I won't do all the math. You take this as your Gibbs energy expression, and you simply want to say the second derivative of delta G with respect to, let's say, xb squared equals 0. Plug this equation into that equation, set it equal to 0, and solve. Remembering when you're doing the differentiation that xa plus xb equals 1, and therefore dxa equals minus dxb when you do the differentiation. Okay, so you set that equal to 0, and that gives you T critical, and what you're going to get is T critical equals omega over 2 R should be the answer you get. So I recommend that you do the differentiation and prove to yourself you can do differentiation and end up with that expression. That is the right one, right. So you see, of course, what this means is the greater is omega. As omega is greater, more and more positive, then you have bigger and bigger positive deviations, which makes the system less and less stable, and so the critical temperature gets higher. And if omega is negative or 0, then obviously you do not have any negative deviation, so you never have a miscibility. And it's going to be set the second derivative equal to 0 when xb equals 0.5. That you do by symmetry. Clearly this is a symmetrical equation, so the it's going to be at 50%. Here, for example, you can't do that. It's not quite so simple, because here, being not a regular solution, the second derivative goes to 0 at a certain temperature, but not at 50%. So I'll give you a homework problem to play with those things. Thank you. This makes life simpler. Any questions on that? Okay, so then for the homework, Series 10, it was 1, 2, 3, 5, 6, and 7. So you could try others if you were so inclined. Come on, open it. Okay, let's do number 1. Okay, number 1 is simply the lever rule. Anybody who needs a refresher on how the lever rule works? Okay, I put this all up on the website. Presume you've looked it over. Are there any questions about it? So just to be sure you understand how the lever rule works. Okay. Any question? Then I shall leave it up to you to look at the answers. Number 2 is also the lever rule. Okay, just be sure you can do number 1. It's straightforward. It's the lever rule, but you understand how eutectic molding works, right? Sometimes what people don't quite understand, maybe I should just mention it, we talked here about the, okay, as you start to cool here, as you reach this point here, of course, imagine you have the sample. Here is your sample, it's all liquid. As the temperature reaches this point here under equilibrium cooling, then you start to get an primary alpha phase forming. And as you cool it down from here to here, the primary alpha phase grows. Okay, by its nucleation and diffusion, and the composition of the solid phase follows this line here upon equilibrium cooling, which means, of course, that within, this is liquid, within the alpha grains, then there must be diffusion towards the surface so that the entire grain remains homogeneous. The lever rule only works if, in fact, all the phases are homogeneous. Now, if you cool this very, very quickly over this temperature range, what happens is at the beginning, when you reach the liquidus temperature, then the interior of the grain is over at this end of the tie line, which is quite rich in A. And then as the grain grows, the solid that precipitates on the outside follows this line and becomes richer and richer. So you have a high A in the middle and then lower concentration of A towards the surface. If this cooling is at one limit, you assume that is very, very slow cooling, so the concentration gradient evens out by diffusion. This is equilibrium cooling. And in that case, when you've reached the eutectic, you have a liquid here in equilibrium with a homogeneous solid here. And so, of course, you apply the lever rule between those 3 points. But if it's been very fast cooling, then the solid is not here. The solid has a temperature, has a composition somewhere between here, average composition somewhere between here and here. At the other limit, where there's no diffusion in the solid state, that's called Scheil cooling. Okay, so that's the other extreme. But of course, if you're doing Scheil cooling, SCH, if you're doing Scheil cooling, then the lever rule isn't going to apply. But you can still do a mass balance with it, but you got to do step-by-step mass balance by an iterative thing. This is how fact stage works. On the Scheil cooling, fact stage will assume that a very small amount precipitates at this temperature, removes that from the equilibrium, and then takes another little bit that precipitates 5 degrees below and calculates the composition of the second layer, removes that from the calculation, moves down, and you can do the shell cooling that way. Okay, so now anyway, here this was equilibrium cooling, so when you reach the eutectic, you have just before the eutectic reaction, you have a solid at this composition right here, in equilibrium with the liquid right here. Then the eutectic reaction occurs, in which liquid gives you the alpha phase plus the beta phase, and this forms the liquid then completely precipitates to form a mixed eutectic mixture, which is, let's say, lamella of successive layers of alpha, beta, alpha, beta, alpha, beta. Okay, so this is called a eutectic grain, but the eutectic grain isn't a phase, it's a two-phase mixture. Okay, so the overall eutectic has this composition. A eutectic grain is simply came from the liquid forming the eutectic. So the overall composition of the eutectic grain is given by this point. Okay, but the grain consists of alpha and beta phases. The microstructural constituents at this point, this is just below T eutectic, the microstructural constituents are the primary alpha grains and the eutectic grains. That's what you see under a microscope. Okay, and the word we use for that is the microstructural constituents are the primary alpha phase and the eutectic. Some people say eutectic phase, but thermodynamically it's not a phase, it's a two-phase mixture. The thermodynamic phases are alpha and beta. This is a two-phase mixture because the alpha in the primary and the alpha in the eutectic are the same phase with exactly the same composition. Thermodynamically, they're the same phase. They're in different places, but they're the same phase. Okay, so your overall eutectic is of this composition, and it consists of alpha and beta. If you want to find the ratio of alpha and beta within the eutectic grain, you take a eutectic grain, and you want to find the ratio of alpha to beta within the eutectic grain. Then you apply your lever rule between this point, and the overall composition of the eutectic. Okay? Okay, so the alpha in the eutectic divided by the beta in the eutectic would be this distance over. If you wanted to find the ratio of alpha to beta in the entire sample, then you apply the lever rule between the alpha composition, the beta composition, and the overall sample composition. Finally, if you cool the thing at equilibrium down from T eutectic to T, actually if you cool it quickly down to TR, nothing's going to happen and you're going to remain with the alpha at this composition and the beta at this composition, because that's not equilibrium cooling, because solid state diffusion is slow. But if you cool it very slowly and then say, or you cool it down to TR and then you anneal it for a long time, what's going to happen now is, of course, the alpha grains, the grains of alpha, are now supersaturated. The grain of alpha here, the alpha primary, overall composition is here, but when you cool it down, you're now in the two-phase region. The alpha has only this composition. So what's going to happen is within a grain of alpha, you're going to have precipitates of small precipitates of beta forming within the grain of alpha. This is, of course, the precipitation hardening is going to make the stuff much harder because dislocations get stopped by the precipitates. Okay, so this would be the beta precipitated in the alpha. What's left here is called the residual alpha. So at T eutectic, the alpha is homogeneous, one single phase at this composition. When you cool it down to TR, to a good approximation, what happens is the total amount of the alpha grain stays the same. Of course, we're making an assumption because as you cool it down, there could be reactions going on across the boundary here, but we assume that's relatively small. What's really happening, the main thing that happens if the thing reaches equilibrium at TR, is that beta precipitates within the alpha, usually on grain boundaries or something. And so you're left with beta precipitate in the alpha, and you're left with a residual alpha. The residual alpha has this composition. The beta precipitate, of course, has that composition. And if you're trying to find within a grain of alpha, you're trying to find the amount of beta precipitated within the grain of alpha, Then you use the compositions of the two phases, alpha and beta, and you use the overall composition of an alpha grain, which is right here, and you apply the lever rule between those 3 points. Okay. And of course, within the lamella, the alpha lamella of the eutectic, you're going to get exactly the same thing. And within the beta phase of the eutectic, you're going to get alpha precipitates. Okay, because the beta phase that was here now has this composition, so you're going to get alpha precipitates within the beta. So you're going to have a residual beta, you're going to have alpha precipitates, but you still, when you reach TR, the thing's in equilibrium, you have two phases. Thermodynamically, you have this phase and this phase. Microstructurally now, it's very complicated. Now you have residual primary alpha with beta precipitates in it, you have residual eutectic alpha with beta precipitates, you have residual beta eutectic with alpha precipitates. But if the thing's totally at equilibrium, you still only have two phases. The lever rule is just a mass balance. Doesn't matter if it's mole fraction or mass fraction. But it assumes that all phases are homogeneous and the whole thing's at equilibrium. If you've got non-equilibrium cooling and you have concentration gradients, or phases are not there in their equilibrium amounts, then it works. Okay, so look over the answers, but that's the main point. Question 2 is also the lever rule. Very simple question. And when I gave this problem over the years to undergraduate students, this is the problem I found that is most poorly done of all the problems in all the problem sets. Because it's simply, people are incapable of changing from mass fraction to mole fraction to volume fraction. I find that with fourth year metallurgists, if you ask them to take an alloy, if say 2-component or 3-component alloy expressed in weight fraction, and ask them to convert it to mole fraction, at least half of them will get it wrong. Okay, so what you have here is you have a lead antimony alloy. It's a simple eutectic system with no solid solubility. Okay, and what's happened is that you cool it very slowly. You cool it very slowly from here down to 25 degrees Celsius. And at 25 degrees Celsius, you observe that you have eutectic grains of antimony. So you're getting a eutectic antimony formed between here, and then here you're going to get eutectic grains. So when you cool the thing down to 25 degrees, you'll find a pro-eutectic antimony, and then you will find a eutectic. Okay, and what they do is then you put this in a microscope. The microscope has a little grid across it. Okay, and you take your microscope has a grid with some little, so you measure across this diameter, you measure how much disc you measure. You take a few diameters across here and measure what fraction of each diameter is covered by the eutectic and by the antimony. And taking the average from this, you can work out the volume fraction. Or generally there's software now that just looks at the two images and works out the surface area for you. Okay, you put this on some sort of image analysis device and it will tell you that 50% of the surface is antimony grains and 50% is pro-eutectic. Okay, so we find that this is by volume, of course. 50% by volume are eutectic grains, which is the two-phase mixture. So remember, the eutectic grains have this composition. The antimony grains have this composition. So 50% by volume is this, and 50% by volume is that. There's no solid solubility. We give you the densities of lead and antimony. The antimony is pure antimony. The eutectic consists of pure lead and pure antimony mixed at this overall mixture. And we simply ask you to calculate the weight fraction or volume fraction. Yeah, well, the weight fraction. Calculate then if it's 50. Can calculate the overall weight fraction of your sample. What is this composition here in weight fraction? Okay, so I'll let you look over the proof for that. Okay, but this is how it works. Okay, converting from your volumes to your weights and so on. Sounds really easy. Okay. I would recommend you take a look at that. Anyway, there was the answer. Try to do it yourself first and then see. If not, you can see the way I did it. And you'll see when you look at the answer that it isn't a two-liner either. The answer actually is answer takes a little bit of calculating. Okay, number 3. Oh, sorry, was that? Yeah, two ways of doing it. Sorry. I think I gave you 2 ways of doing it. All right, question 3 was the various cooling curves, and I asked you to draw the phase diagram that results from those cooling curves. Okay, so we'll do a so you had this two-component system, and you did some equilibrium cooling curves. You all know what thermal analysis is. Okay, so equilibrium cooling curves. This was temperature versus time. And you have things like this, in which ideally at the liquidus you're going to get a change in slope, and at the eutectic you're going to get a plateau. The reason being, now if you take this is your furnace here, this is the furnace, this is your sample, you put a thermocouple in the sample and you cool it down slowly with some stirring. So you lower the temperature of the furnace is going down slowly. When the thing starts to solidify, it gives off heat, and that slows down the cooling within the sample. The furnace is cooling outside, you're slowly ramping down your furnace. Okay, but the sample now is going down at the same temperature as the furnace, but when the solid starts to precipitate, it gives off heat, so heat is being generated within the sample, and that slows down the cooling within the sample. Okay, so you get a change of slope. Ideally. When you reach the eutectic temperature, then of course the temperature remains constant. The system gives off heat such that the temperature always remains enough heat to keep the temperature constant until the entire liquid is solidified, and then it cools back down. Of course, this only happens in textbooks. What really happens is that you have supercooling. The liquid, you need nucleation, so the liquid persists below the melting, below the eutectic. You reach the eutectic, the liquidus. You reach the liquidus here, and the liquid should start to, the solid should start to precipitate, but in actual fact it doesn't, because it hasn't nucleated yet. So what happens is the temperature actually continues to drop for a bit, and then finally you get some nucleation. Now the thing is below where it should be, so much heat's given off that the temperature goes back up. All right. Now in principle, then the temperature should go, if this is the liquidus temperature, you might hope the temperature would go back up to the liquidus, but of course it never does, because by now the temperature is already quite low. Okay, so what happens is it comes back up a bit and then kind of cools off again. So the question is now, where is the liquidus, you see? Now if you do, this is called thermal analysis, not differential thermal analysis. This is good old-fashioned thermal analysis with a great big sample, and you're cooling the thing. Okay. So you're going to get a curve that looks like that. Now, if you haven't got too much supercooling, what you can do is, it's usually fairly obvious how this thing can be extrapolated back up. It's not a straight line, but usually it's not too bad. If you get a little bit of experience with this sort of stuff, you can get it back up to where it would have transformed, okay? But it isn't evident, it's not a straight line, and it never comes back up to that temperature. You try to minimize as far as possible the amount of supercooling. One way of doing this, of course, is to be sure this thing is stirred. It has to be, if there's temperature gradients in there, then you're going to have trouble too. But if you don't have temperature gradients, you keep it stirred to keep the temperature gradients even. This is generally easier with a metal than, say, with a non-metal like a salt or an oxide. But you also try to favor nucleation. One way to do that might be to put some nucleation sites in there, like a little bit of sand or something. But what is found, and there's even been controversy today, is that if you shock the thing, if you give it a good whack, suddenly you take the whole furnace, they say, or you take the sample and you agitate it, and suddenly you'll see the supercool, it nucleates, and this thing shoots back, the temperature shoots up. The theory of that is that you're initiating shock waves locally, which raises the pressure locally, and higher pressure favors the formation of the solid phase. So just just locally in a very small region, you form a nucleus by the high pressure, and then that nucleus grows. Okay, but with the metal, without supercooling, without stirring or shocking it, it's quite easy to get supercooling of 20 degrees. And the temperature never comes back up again. Okay, so you've got to be, supercooling can be a big problem. And you also get supercooling when you hit the eutectic, because now, although you've got the, say, the alpha phase is forming, the beta phase has to start to nucleate as well. And that doesn't happen either. Now this is usually easier though, because as long as you're fairly close, you got enough sample, you do actually reach the, more or less the line. So it comes back up to the actual eutectic temperature in most cases, but not always. But the liquidus temperature is the hardest one to do this way. Anyway, in this particular thing, I gave you some, just to go through this, I gave you some equilibrium, some ideal cooling curves. So here you had a change in slope here, and you had a plateau, so this was obviously a liquidus and an invariant. Here you had just a plateau, meaning there was no primary phase, there's just the eutectic reaction. Here there's a liquidus and an invariant, but these are all the same temperature, so it's clearly the same invariant. So here, this is a quasi-unary system, the congruent melting point of a pure compound, which melts with the plateau like a pure material. Okay, here you got a plateau for the pure material melting. Here you got a change of slope in the plateau. Just a plateau, because it's the eutectic change of slope in the plateau, so you've clearly got something like this. I've drawn the solid solubilities with dotted lines because this from these results, you really can't tell what the solid solubility is. If you look in the book, it's very, very small. It's almost stoichiometric, but you can't tell that from here. Now, you might hear this, you'll see this too in the books. They say, well, look, here at least you got here we got a eutectic reaction. So clearly the solid solubility is at least to the right of this point. But this is, again, depending upon, you're hoping that you have complete equilibrium. Okay, if it were not to the right of that point, the phase diagram, if the solid solubility were more, then you would have a curve like this, you see, and you would have this would come down here, and you would have a change of slope here and a change of slope here, and you would never, you'd kill down here, you never see the eutectic. Okay, but in practice you may actually see the thing if the thing's not really at equilibrium. Okay, so in fact, you usually will see it. You will also see in the books that, well, suppose you do reach this, okay, suppose you do have a case like this, you're trying to, you have a liquidus and a solidus. The ideal cooling curve, of course, then, as you're cooling it down from here, is you cool the liquid, then here you get a change of slope at this composition, and then here, where the solidification stops, you get a change of slope back the other way. Well, you'll never see that. I mean, this goes like this. Right? You'll never see it, because what's happening is the closer you get to this point, the less and less solid there is left to precipitate. It never changes abruptly in this guy. It's off, okay? Also, cooling curves. If you, let's say I do a cooling curve over here. And I do another cooling curve at this composition, and I'm trying to find the liquidus temperature. All right. What's important is how sensitive is the thing. Remember how these, I'm telling you this because I find the thermal analysis experiments are really badly interpreted by people. I can give you a very recent consulting job I did, which was shocking by people, I won't mention the names. Is this liquid is here, okay, let's say the liquid is here is much flatter than the liquid is here. This is the case. As you get down to the eutectic, the liquid is generally tends to be more vertical. Right? So liquid is up here is quite flat, and down here it's dropping very rapidly. Which is going to be easier to measure, this point or this point, and why? By the cooling curve. Remember, you're going to see the change of slope. The temperature time is going to go like this. You want to see that change of slope, which is going to be the hardest. This one will be easier. The reason being, you just think of the lever rule. It starts here. Remember, what you're really seeing is you're seeing the heat effect. The heat is being given off, and that slows down the cooling. So you need enough heat to be given off in order to see something. Now if you're up here, the liquid that starts here, supposing you cool it, say 5 degrees. You cool 5 degrees. Now after cooling 5 degrees, by the lever rule, the amount of solid to the liquid is this distance over this distance. In other words, quite a bit of solid has already precipitated during a 5-degree drop. So you cool the temperature a small amount. Since this is very flat, you get quite a large amount of solid precipitated within 5 degrees, so a lot of heat is produced. So the amount of heat, joules per degree of cooling, is large, and so you get a big change of slope. But here, where the liquidus is very steep, you might cool the thing by 5-10 degrees and you've only got a very small amount of solid which precipitates by the lever rule. So the percentage of solid, grams of solid per degree of cooling is very, very small. And what happens is the change of slope is so small you can't see it. So a flat liquidus is very easy generally to measure by a cooling curve. A steep liquidus is very difficult to measure by a cooling curve. Soliduses are very, very difficult to measure by a cooling curve. People will try to do heating curves to get the solidus and the eutectic. Heating curve is absolutely no good for a liquidus. It's not too bad for a solidus. You notice the temperature at which the liquid starts to melt. Okay? The solid starts to melt, and so you'll see a change in slope as you heat it. But then it's the same thing. As you heat the liquidus, you're not going to see that because that's just kind of the end of the reaction. Seeing the beginning of the reaction is easier than seeing the end of the reaction. A heating curve to get a eutectic is sort of okay, but it requires the eutectic reaction is liquid gives you alpha plus beta. If you're going the other direction, what is the alpha? It's only at the points of contact between the alpha and beta phases that you're going to get fusion. Okay, so you're not going to get an awful lot of, there's a kinetic restriction here. It doesn't suddenly all melt. It melts at the boundaries, so cooling curves are better, I think, for liquiduses and eutectic. Heating curves are going to be better for solids. This now brings us to differential thermal analysis. You all know how differential thermal analysis? This was straight thermal analysis. When you do straight thermal analysis, you do temperature versus time, and you see the thing, and you also see you'll see your supercooling. Okay, now you do differential thermal analysis. Okay, what you're doing is you're measuring the temperature of the furnace outside, and you're measuring the difference in temperature between your sample and between your sample and the reference. It doesn't change state. What do you see? You cool the thing down, and then you get a peak. Okay, this is the heat. This is an exothermic peak. This is your time here. This is or the temperature of the furnace. And this is your DTA signal, so you get a peak. Okay, so where then is you take your liquidus? People will take this to be the liquidus. This is your temperature of the furnace. This is T. Where you're measuring temperature and then you're measuring the DTA signals. This is your temperature. So T of the sample. This is one thermocouple is measuring the T of the sample. And this is your delta T between your sample and your reference. Okay, so you see the effect going on here. The idea is you magnify the effect, blah, blah, blah. Okay, but where do you take, there's no way you can figure out what the, see, because the temperature is actually going back up, but you don't see that here. It goes this way, and are you getting this temperature, or are you getting this temperature? It's hard to see the supercooling. Should you be taking that temperature when it starts? This temperature, when something happens, will be this temperature. Okay, where is your bloody peak? So, think about it. How do you interpret your DT? And upon heating, well, again, what happens? Where? Because you're not really seeing, in a thermal analysis, you see what's actually happening. Here you're seeing the temperature of the sample, which is a small sample, so you're never going to see it really being reheated. I think these DTA measurements are all badly interpreted. This course is not supposed to be all about that, but when you look at DTA, really think about what are they getting? What are these peaks? Think of the supercooling, and are they really seeing the supercooling? And how is this thing being interpreted? Because they just take the peak, the top of the peak, and I have no idea what the top of the peak corresponds to necessarily. That's just the temperature where it kind of reached its maximum again. That's kind of probably this temperature somewhere, but not exactly either. So, I don't know. And heating and cooling curves are different. And I've seen so many papers where people just take the top and it's not right. DTA is really, really fast. Take a little bit of sample, you put it in your machine, you push the button, you go wait for coffee, you come back and it's got your answer on the graph. Okay, and that's why people like DTA. Thermal analysis takes a lot longer. Some people don't like to do it. But, years ago, the American Society for Metals had a program, the alloy phase diagram program, where people worked to try to evaluate and compile all the phase diagrams of alloys known to mankind. So we did a lot of them here. I did 200 or 300 looking at these, and so going back to all the measurements that have ever been made of the binary system phase diagram. And I found this, and many of the other editors found it, that if there's, say, the same diagrams, well-known diagram, important diagrams measured by 8 or 10 different authors from 1920 up to 2000. And we found after we did the evaluation and all that, that very often the older measurements were the ones we went with. They're better. Simply because they were, people had a lot of time, they took a lot of care. Okay, the more people put your thing in, your thermal analysis, your DTA equipment, and you end up with 300 liquidus points, but they're all not right. Okay. So the more DTA they had, the more DSC, differential scanning calorimetry, in general, unless it was a really good experimentalist, the worse the results were. You had a lot of results, but the accuracy was suffering. Okay, that's my tirade against badly interpreted differential thermal analysis and differential scanning calorimetry. Thermal analysis sounds so straightforward and simple, and it really can give you really bad results. Okay, but any questions about this particular one? All right, let's do the other ones fast here. Number 3, what do I have? 5, 6, and 7. Okay, find me the errors in this diagram. Here's an error because clearly eudectic has to be. Okay, there's one error, here's another error, these two lines have to go together. This is an error because if there's a maximum point, when you have a maximum in a two-phase region, the maximum has to, the point where the two line, where the solidus and liquidus contact has to be at the top, and it actually has to contact. Okay, so here the two lines don't contact, here the two lines contact, but not at the maximum. So the two of them have to contact at the maximum, and even with zero slope, as I showed you. When the two reach the maximum point, this is the maximum temperature, and both curves have a zero slope. They do not come up like that. Okay, this is an error here because this line should not extend this way. This line should extend into here. This, I guess, is an error because you have 4 phases in equilibrium at one temperature, although in principle, if the pressure were exactly right, you could have 4. Phase diagram is at constant pressure. So this would really be 2 invariants, but there will be a temperature in which, pressure in which they would be exactly the same, but that's an error. This is not an error. There's no reason why this can't go back. This change in slope here, this can go, called retrograde solubility. Usually it will go this way, but I mean, thermodynamically there's no problem there. And I don't know, number 6. This was from my undergraduates, but if you just label the 1 and 2 phase regions, well, it's just that as you go across the diagram horizontally, you go 1 phase, 2 phase, 1 phase, 2 phase, 1 phase, 2 phase, 1 phase, 2 phase. Now you may come across a line like this is a 2-phase region. That's a 1-phase region. It's not a line separating two two-phase regions. It's a very, very narrow 1-phase region. So you're going 1 phase, 2 phase, single phase, double phase, single phase, double, single, double, 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 and you should end up with a single phase if you're around.
Mr. Belton?
Yeah.
For the number 5, just want to verify. Did you mention the gamma on the left side? Is it possible that it's lower?
Sorry? This is wrong. This is wrong here.
Okay, it
Yeah,
should
they must
go
touch.
higher.
They must touch. They must. This line and this line must be contact at one point,
Okay.
and that point must also be the maximum. So here they don't contact at all. Here they contact, but not at the maximum. So these are 2 errors. This is an error, and this is an error.
And yeah, just mentioned that it's the contact on the XB equals 0 should be higher. Is it another possibility? That the
This should, oh yeah, okay, I suppose these should go up like that.
Yeah.
Okay, that's awesome. Just whatever, however you want to correct it is okay, but this is wrong.
okay.
And finally, there was a simple peritectic diagram. This proves actually you can have, this is a peritectic, but there's no compound. So if you have an incongruently melting compound, you get a peritectic, but you can have a peritectic without having an incongruently melting compound. And at several different temperatures, T1, 2, 3, 4, 5, 6, 7. I plotted here the so if you take a look at that. If you have any questions, let me know. That's pretty straight. It's just the disposition of the three curves. You have an alpha curve, a beta curve, and a liquid curve. I drew the alpha and beta as two separate phases, not as a miscibility gap, but as two separate phases. The only difference here is you have the three phases. You have your alpha, your beta, and the liquid. As you raise the temperature, the liquid descends relative to the alpha and beta. Okay. The point is that when you reach T4, which is the peritectic temperature, you imagine going from T1 here that the liquid phase is above the solids everywhere. Then as you raise the temperature, imagine the alpha and beta phase remaining more or less, the curves remaining more or less unchanged, and this entire liquid curve decreasing, going down, until you reach the peritectic, which is T4. And then you have this, but now they meet, but they meet in the order liquid, alpha, beta. In the eutectic system, they would be alpha, liquid, beta. Here, just because of the shape of the curves, it's liquid, alpha, beta. Okay, so you have your peritectic, but the liquid phase is on the left and the two solid phases are on the right. That's it. All right, that's what I want to say. Any questions about number 10? Actually, since you're all doing phase diagram analyses, I don't have really time to go into this. I would highly recommend that you find yourself a book on phase diagram measurements, techniques of phase diagram measurements. I could give us a lesson on phase diagram measurements, but find yourself some book on phase diagram measurements and really read about the different ways of measuring phase diagrams and the error limits in them and so on. It's not trivial, and especially with DTA and DSC. Resistance measurements, solubility measurements, and so on. Okay. I think we don't spend enough time on this when we have people doing optimizations. We have you spending all your time thinking about the theory and the mathematics and the models, and not actually about. I mean, we're supposed to be doing evaluation of the phase diagrams, and evaluating the phase diagrams means you got to also think about the experimental techniques and their accuracy. And to do that, you've got to understand how they do the experimental techniques. So I really recommend trying to find a decent book on experimental techniques, and I can actually give you a little something I wrote once. I'll try to remember that for next week. All right. Question? All right, I'm going to talk about, if you get out this thing here, I'm going to talk about section 3, which is the Gibbs phase rule. Starts on page 25. It's possible, yeah. Solubility decreases? Well,
Increases.
yeah, as I said, well, that was the example I showed there called retrograde solubility. You can have a temperature composition. I mean, normally you have a diagram that look like this. So the solubility decreases as you go down, but it's not necessary. I mean, it is possible for that to go like that. Thermodynamically. You rarely see that, but it's possible. There's no thermodynamic reason why that can't happen. There's like physical reasons, is that you get lower and lower temperature, the entropy becomes less and less important. So things tend to, it's the entropy that's making it soluble generally, and it's the heat that's making it insoluble. So as you lower the temperature, it's going to become less and less soluble. The energy effect becomes more important relative to the entropy, the disorder, but it doesn't have to be. And there are cases, I can show you some cases that actually go around like that. This, however, still has to extrapolate into there. Okay, it can't start out like this. Well, it actually could start out with a negative slope, but this still has to extrapolate. It could even start out like that with a negative slope as long as this extrapolates into there. This would be due to a very big delta Cp. You could actually imagine that you have not imagine, there will be cases in which the enthalpy is so temperature dependent that it actually causes this to happen. You can even see miscibility gaps. I've never seen them in a metallic system, but if you have temperature composition, normally you have a liquid and then you have two liquids, and this is your critical point of your miscibility gap, which then gets wider and wider. Okay, but you can actually get this coming around like that, and you can have a lower critical temperature. So here the liquid is completely miscible, and as you heat it, it becomes immiscible. And there are examples, I think water and nicotine actually looks like that. And I've also seen some that don't go all the way, but they come in like this and then come back out again. These are generally in organic systems, and it's generally due to some complex entropy effects and complex packing structural effects of long chain molecules and so on. And simple systems, I've never seen anything like the sort of systems we're going to be dealing with ionic salts or oxides or metals or so on. I've never seen that, but again, thermodynamically, it's quite possible. If the excess Gibbs energy, remember, you got a positive thing here because you have a positive excess Gibbs energy. But now, if the excess Gibbs energy varies so much with the excess Gibbs energy itself becomes less and less positive as you go down in temperature because of an entropy effect, then it's going to come back around again. So thermodynamically, you even will see this, but they're considered to be curiosities rather than anything you have to worry much about. Okay, the phase rule. Okay, you've all seen the Gibbs phase rule, right? F equals C minus P plus 2. Is that the way you've seen it written? All right, this seems very simple. Everybody understands the Gibbs phase rule, but this can also be very deceivingly simple. Okay, C is the number of components in the system, P is the number of phases at equilibrium. This only applies at equilibrium when the system's at complete equilibrium, right? If the system's not at equilibrium, the Gibbs phase rule doesn't apply. F is the number of degrees of freedom, and that's the number of variables that you can vary independently and still remain in the phase region that you were in. Okay, now let me show you what that means, the normal interpretation of that. Let's say we have a binary phase diagram between A and B versus temperature. We'll do a very simple one like this, and here you have the eutectic. So here you have alpha, beta, and liquid. And we'll suppose that pressure, this is pressure. The problem here, P can be the number of phases, it's also the pressure rate. Pressure equals constant. Okay, so say we're up here. So the number of components in this system is 2, the components are A and B. Okay, the number of components is 2. If I'm, let's say, at this point up here, okay, the number of phases equals 1. I'm in a single phase region. And so F equals 2 minus 1 plus 2 equals 3. So I have 3 degrees of freedom. Now I fix the pressure as constant. This diagram is constant pressure. Okay, so with the pressure constant, this is reduced to 2. And what does 2 degrees of freedom means? That means that I can change the temperature and or change the composition and still remain in that one phase region. So I have two variables that I can play with. If I am here, I have alpha plus liquid. Now the system's at equilibrium, so you have this phase at this composition, in equilibrium with this composition and this temperature. Okay, so at this point here, at that point there, I would have F equals 2. I have the number of phases, and now the number of phases is 2. So F is 2 minus 2 plus 2 equals 2. The pressure is constant, so I have one degree of freedom. Now what are my variables then? That means I have one variable that I can choose independently. My three variables are the temperature, composition of this phase, and the composition of this phase. And I want to be in that two-phase region. I want to be in the alpha plus liquid region. Okay, I want to be in the alpha plus liquid region. I choose one variable. I can choose this temperature, of course the temperature can't be down here, but I have at least a range of where I can choose the temperature. But if I want this to be the temperature, if I want the temperature to be 1002 degrees, and I want to be in the alpha plus liquid region, then I have no choice about the other two variables. The composition of the solid will be here, and the composition of the liquid will be here. Okay, I can choose the temperature, but that's it. The other variables are chosen by nature, by the system. Okay, so the number of degrees of freedom is 1. Or I can say I want to be in the two-phase region, and I would like the liquid to be 48% B, for example. In that case, I can choose the liquid here, but now I have no choice about the temperature or the composition of the solid. If the liquid is going to be 48% B, then the temperature must be 1002 degrees, and the solid is going to be at that point, and 1 degree of freedom. Now, if I change the pressure, of course, I have 2 degrees of freedom because of the pressure will have an effect on the diagram when I change things. Now, people say, well, look, I can change the composition. The overall composition can vary anywhere from here to here. I can take an alloy at 20%, or an alloy at 25%, or an alloy at 28%, and I still stay in the two-phase region at 1002 degrees. That is not a variable in the sense of the phase rule. The overall composition of the system is not a variable. The variables are the compositions of the phases, not the overall system composition. Okay, so when you say what variables can you, gives you the number of variables you can independently select. You have to list what I mean by variables, and the variables would be temperature, pressure, compositions of the phases, but not the overall composition. Okay, that's something that's usually missed. Okay, I can change the overall composition anywhere between here and here, but that doesn't matter. The compositions of the phases are fixed. If I have exactly the eutectic composition, I can have 3 phases in equilibrium if I'm exactly at that point. Now I have 3 phases in equilibrium, so the number of degrees of freedom drops to 0. That means if I want to have 3 phases in equilibrium, I have no choice. It must be at the I must be at the eutectic temperature. The alpha, liquid, and beta phases must have those compositions. No variables can be fixed, are free to choose. Any slight variation from those 3 and I won't be in the 3-phase region. Once again, the overall composition doesn't matter as long as it's between those 2 limits. Alright, well, that looks straightforward. Now let's say, okay, I'm just going to, before I go formally into the phase rule, let's say I take a 1-component system. So I have C equals 1, let's say I take H2O. So now here I plot a pressure-temperature diagram, and you all know the pressure-temperature diagram, solid, liquid, gas, okay? Okay, so now, if I'm, now the number of components equals to 1, so F equals 1 minus P plus 2. Okay, so if I'm in a 1-phase region, over here I'm in a 1-phase region. Okay, so if I'm in the 1-phase region at this point here, F will be equal to 2. And so I can change pressure and temperature as I wish. If I'm on a line, I'm on a line, I have 2 phases in equilibrium, so on the line F equals 1. So if I want to remain on the line where the 2 phases are in equilibrium, I can choose a temperature, but then the pressure is chosen for me. I can choose a pressure, but then the temperature is chosen for me. Okay, 1 variable. And of course, if I'm here, I have 3 phases at equilibrium, so F is 0. So if I want 3 phases at equilibrium, I only have 1 choice. Now, you'll say, but it's H2O. Looks to me I've got hydrogen and oxygen, so why don't I have a 2-component system? Okay. I can say my components are hydrogen and oxygen, and now the whole thing kind of falls apart. But what I'm in here is I'm in a quasi 1-component system, which means that Every phase, anywhere I am in the diagram, every phase has exactly the H2O. The ratio of hydrogen to oxygen is H2O in every phase. In that case, this becomes a one-component system. Okay? Because every phase follows the same stoichiometry. I'll say this actually here on page 25. Okay. The number of components. This is really the formal definition of the number of components. This is the number of substances required to describe the elemental composition of every phase present. So for pure H2O at 25 degrees and 1 bar pressure, C equals 1. Okay, for a gaseous mixture of hydrogen, oxygen, and water vapor at high temperatures, C would be 2. Now you think there, well, this could be many species in the gas. There's oxygen, hydrogen, H2O, O3O, H3O, and so on in small amounts. That doesn't matter. It's the, but to fix every phase, you would only have to fix the amount of hydrogen and the overall hydrogen amount and the overall oxygen amount, and the amounts of every other phase would be fixed by various chemical equilibria. Okay, although there are many species, these species are all at equilibrium. At a given T and P, it is sufficient to know the overall elemental composition in order to be able to calculate the concentration of every species. So if I told you I had water vapor and I told you how many moles of H there were and how many moles of O there were, you could then calculate a chemical equilibrium, the number of moles of H2O, H3O, O3, O monatomic, and so on. Okay, you can never, the number of components can never be greater than the number of elements. Okay, you can't get more than the number of elements. Okay. So you should read this over carefully and look at the various figures in order to give you the number of components. Now, I want to underline this whole thing about the back here to the then we're back here. We had this figure. Okay. So again, it's the number, or the other way of looking at the number of components is the number of components in the system is one more than the number of composition variables required to tell you the composition of every phase. Okay, so if I have pure water, H2O, the number of composition variables is 0. I don't need it. Every composition is 100% water. Your one component system. If you take a binary system, you plot A versus B, then you need one composition variable, so you have a two-component system. Okay, but now you've got to be careful again about the definition of every phase. Okay, here we have an isoplethol phase diagram of the zinc, magnesium, aluminum system. This is a section. Here's your zinc, magnesium, aluminum system in figure 2, and I'm plotting across this dotted line, I'm plotting composition across this line versus temperature, which is vertical. Okay, this is an isothermal section, but going along this line, we're going vertically. And that then gives us this figure. Okay, this is vertical as temperature, and here you have the molar ratio along that line of 10% zinc. This is 10% zinc. Now you would say then, well, you only have one composition variable. Going from one end to the other, one composition variable is defining the system. But it's not. One composition variable is defining the overall composition, but it's not telling you the composition of every phase. Okay, because the tie lines don't necessarily lie along that line. As I went through last time, if you are, for example, at this point P, which is on this dotted line, the overall composition is at point P, but your two phases are a tau phase here and a gamma phase here. Okay, and their compositions are not on that line. So the composition variable along this line is not sufficient to define the composition of every phase. Okay, so to define the composition of every phase, you need three component system. This is a three-component system, and if you're doing a phase rule analysis of this isoplethol section here, it is a three-phase system. Now, there are some cases in which, in fact, all the tie lines do pretty much lie on the isopleth. Okay, and I showed, for example, the other day, if you have the system silicon, say oxygen, calcium, silicon, and you go from CaO to SiO2 along this line here, just about every phase, if you have an overall composition here, it's still the two phases that equal the tie line is going to be along the same line. All your phases are somewhere in the calcium silicate. In that case, if you draw temperature versus CaO, SiO2 along this line, you do get a diagram that obeys the phase rule for 2. Okay, that's a quasi-binary system because every phase is given by that one composition variable. Or you can define your components as CaO and SiO2, and every phase can be, so you have phases like Ca2, SiO4, they can be defined, that can be defined in terms of the 2 moles of this and 1 mole of this. So there's your. Okay, so now I want to derive the phase rule for you. So we'll go back to page 25. You have it? Okay, I'm also reading here from page 25. It says there's generally more than one way to specify the components of a system. For example, the iron silicon oxygen system could also be described as the FeO Fe2O3 SiO2 system. So if you're dealing with the here you have silicon, iron, oxygen. Here I could plot FeO. This is Fe2O3. Here I have SiO2, so I could draw this triangle. And any point within there could be defined in terms of the amounts of iron, silicon, or oxygen, or with respect to the amounts of those. Okay, so I could use these 3 components, or I could use these 3 components. It's arbitrary. And you can even define a component, you can even define a composition out here in terms of these 3 components, as long as you're willing to have a negative amount of Fe2O3, which is okay within the phase rule. You can have silica, FeO, and a negative amount of Fe2O3, which would put you over here, and you're still okay. So there are many different ways to arbitrarily define the components of a solution. Clearly, though, in every particular case, there's usually a best way, the simplest way of doing it, and you generally try to avoid negative mole fractions if possible. Okay, but there's no real reason why you would have to avoid negative mole fractions. Okay, so let's go to the... Okay, so I'm going to derive the phase rule in a way that, general way that you haven't seen it done before. So we'll number the components 1, 2, 3 up to C, which is the total number of components, and the phases are alpha, beta, gamma. Most derivations of the phase rule, people only talk about TP and composition, but I showed you 2 weeks ago phase diagrams which had total pressure, which had chemical potential, which had enthalpy, volume, and so on. We want to look at general phase diagrams, not just simple temperature, pressure, composition diagrams. So we're going to try to make the thing more general. So I'm making here a list of the variables that are important in the phase rule. So your variables are temperature, pressure, composition of each phase. Okay, so this is the mole fraction of component 1 in the alpha phase, the mole fraction of component 2 in the alpha phase, and so on. I've only got up to C-1 because only C-1 are independent. This is the mole fraction of component 1 in the beta phase, and so on. You have the chemical potentials, mu1, mu2, mu3. I do not write mu1 alpha, mu1 beta, mu1 gamma, because when the system's at equilibrium, they're all the same. Mu1 is the same in all phases. So there is only one variable mu1. There's not mu1 alpha, mu1, because they're all equal. Same. For the same reason that every phase is at the same temperature, every phase is at the same pressure, every phase is at the same chemical potential. We would also like to look at the total molar volume of phase A, B, or the total volume, if you like, of phase alpha, beta, gamma. I'd like to look at the entropies of phase alpha, beta, and gamma. These are the ones we're normally going to be dealing with. Now I said where the entropies, you could use H rather than entropy. What do I mean by that? I simply mean they're not independent. If we're going to look at the, if we're looking at the chemical potentials as the variables, the Gibbs energy of the phase is the sum of xi. The Gibbs energy of phase alpha is sigma xi mu I. Okay, and that's equal to h of alpha minus ts of alpha. So if I've given all the mu's as variables, That gives me G. If I then choose S, well then H can be calculated. Or I can, so on. If I assume S, H is not independent. If I got all the mu's in S, I have H. Or vice versa, if I want to define H as my variable here, then I have the S. All right, so those are all my variables. Once again, it must be stressed that the overall composition is not a variable. The composition variables are the compositions of the individual phases. The total number of variables is then the sum. So you have 2. Here you have P phases and C minus 1 variables for each phase. And here you have C variables. Here you have P, and here you have P variables. So you add them all up, and this is the total number of variables in that list. Okay, at equilibrium, the chemical potentials of each component is the same in all phases. Okay, so now every chemical, thermodynamically, chemical potential can be written as a function of temperature, pressure, and composition. You may not know what it is, but there is an equation. If I have a phase has a certain temperature, pressure, and composition, it will have a certain chemical potential, so there's an equation relating all those variables. There's an equation relating all the beta variables, and that's equal to this mu I. Okay, so this yields PC, or equations relating the variables. I'm just doing the same thing in algebra. If you have 3 variables, x, y, z, and you have 2 equations relating the variables, then you have one variable can be chosen. Okay, if I write x plus y plus 2z equals 7, and 3x plus y plus z equals 0, and I can choose one of x, y, and z, and the other 2 are good. Okay, so the number of degrees of freedom is simply the number of equations. It's the number of variables minus the number of equations relating the variable. Okay, so here we have PC equations saying that the chemical potentials are all equal in every phase, and the volume of every phase is a function of temperature, pressure, and composition, as is the entropy. This yields an additional 2P equations, so we take the number of variables minus the number of equations, and we end up with F of C minus P plus 2. So that's it. Okay, so now after a break I will go through a few examples of this, though, to show you how it is in fact useful and how you can get confused. Okay, let's take a break. Oh, over here, right? 1, 2, 3, stop.